Today we will discuss about the electrokinetic phenomena. And this is very important basically in the field of colloidal and interface science, and also having important applications in electrical WS as well. And this electrokinetic phenomena is basically concerned with flow properties of colloids, and also we provide the stability of the colloidal systems. The transport of matter and electricity from one phase to other is basically involved in these electrokinetic phenomena, or you can say electrokinetic effect as well. To understand this, we will consider a system. Suppose this is a system, and it is made up of, suppose, two compartments, or you can say two vessels also, which are being separated here. These are simply separated by this porous wall, or simply by a capillary, or you can say a capillary. And it is basically assumed that the temperature and the concentrations are uniform. It is very simple. When this is a porous wall or a capillary, the temperature here in this compartment, suppose this is compartment 1 and this is compartment 2, will be uniform. And similarly, concentration, we are considering this case, concentrations are uniform throughout the system basically. But these two systems, that means, are these two compartments, they basically differ only with respect to pressure and electrical potentials. This is very important. You have to remember these pointers, that in these compartments pressure and electrical potentials can vary, but the temperature and concentrations are kept uniform. Now we know from the previous knowledge the entropy production due to transfer of the constituents, suppose from this vessel 1 here to vessel 2nd, or from compartment 1 to compartment 2, is simply given by this simple relation. We have already done this. If you still want to clarify, please go through the previous videos and you will find this entropy production. So it is simply given by this relation 1 upon T summation gamma A gamma and the zeta of the gamma component, and here we will simply put a bar here which will simply designate electrochemical affinity here. So it can also be written as 1 upon T. This extent of reaction or d zeta gamma can simply be replaced by with the change in the number of moles. Suppose if the number of moles or transfer is taking place from compartment 1 to compartment 2nd, we will simply write it as T and first. Suppose this is number of moles. Okay. So here this A gamma is basically electrochemical affinity. Corresponding to the transfer of the component gamma from phase 1 to phase 2nd. So that means this electrochemical affinity will then be defined as, we will define this simply, this A gamma can also be written as, this is A gamma plus Z gamma F phi 1 minus phi 2nd. These phi 1 and phi 2, these are simply the potentials of phase 1 and 2nd respectively. That means this can also be written as, in terms of chemical potential, we know it can be written as mu gamma phase 1 plus Z gamma F phi 1. That means for phase 1, and similarly for phase 2nd we can write it as mu gamma 2nd plus Z gamma. F is simply Faraday here, and second, because in this case we are considering that the pressure and electrical potentials can change. So we can simply write it as this relation. Here this Z gamma is basically equal to simply charge number, or you can say electrovalence. Electrovalence of the ionic component, which is simply transferred from phase 1 to phase 2 or vice versa in transfer. Here this F is simply Faraday. We know 1 Faraday is basically equal to 96485 coulomb per mole. It is this much of charge. So for simplicity of convenience, we assume that the system as a whole is closed. And the degree of advancement of phase change is given by. We are actually considering that the number of moles are being transferred, suppose from phase 1 to phase 2. So that means in the phase 1 the number of moles will change. So we will write with the negative sign. Will be equal to the number of moles in the second will be equal to this extent of reaction. This is equation. If we focus on equation 2 here, this can be also written as simplified. That means we can simply write this electrochemical affinity will be then equal to, we will basically separate the chemical potentials and potentials of the two phases. So we can write mu gamma for the first phase minus mu gamma for the second phase plus the electrovalence. This is same for both, and F is also, we will take that outside and we will write the potential difference basically. So this is equation. Or we can simply write it as change in chemical potential. That means delta mu gamma plus Z gamma F and delta phi. That means the change in chemical change in potential. So this is change potential difference delta phi. Okay. Now since the temperature and composition, that means we in the beginning of this lecture considered an assumption that temperature and the concentration remains uniform. So here simply the temperature and composition are same in both the vessels. We have then that means this change in chemical potential of the gamma component will be equal to, simply it will be defined by simply changing pressure. Why? Because we know if we take an ideal gas equation, P is equal to nRT, we can write P is equal to n upon VRT, and P is equal to, this defines the concentration, so it will be CRT. That means this pressure will be directly proportional to concentration or temperature here. So we will simply replace it with here delta P. So the mu gamma here, it is specific molar volume of component gamma. That means we can write the equation 1 as, that means now the entropy production, rate of entropy production, which is sigma, it will be dis upon dt, which will be then equal to minus 1 upon t summation gamma dn gamma for the first compartment or first phase dt delta p minus 1 upon t gamma z gamma f dn gamma first upon dt delta phi. That means we can simply define the fluxes as then. That means from the equation 7 we can take this much negative and summation of this much equal to simply J. That means we can simply write J will be simply equal to minus summation of gamma mu gamma dn gamma 1 upon dt. And similarly we can define this current flux here minus summation gamma z gamma f and dn gamma first upon dt. Here this I is simply equal to electrical current due to transfer of charges from simply vessel 1 to vessel 7, and J is simply the resulting flow of matter. Now we will simply keep this in mind and write the equation for entropy production. Entropy production, that means equation 7, becomes, that means the rate of entropy production means sigma will be equal to dis upon dt will be equal to j delta p upon p plus I delta phi upon t. This is equation 9. And we can simply write the phenomenological equations as, that means we can write this I in terms of L11 delta phi upon T plus L12 delta P upon T. Equation 10. And flow of matter as L12 delta phi upon T plus L22 delta P upon T. This is LF. I have to also remember that the Onsager relation basically, which is the L12 phenomenological coefficient, is that L12 is basically equal to L21, also holds good here. We have to remember this also. Now we have basically dealt with here two irreversible processes, one involving the transfer of matter under the combined influence of difference of pressure and flow of electrical current due to the difference of electrical potential. And we also have from this Onsager relation the cross effect of coefficient, that means this L12 is equal to L21, which is basically due to the interference of two irreversible processes. Now we will see here various kinds of electrokinetic effects. One is called streaming potential. Streaming potential. It is represented by a symbol simply SP, and second is called Electro-osmosis, which is represented by EO, and third is called Electro-osmotic pressure, represented by EOP, and fourth one is called streaming potential. Streaming potential, we have already saw this will be the streaming current. Streaming potential is first one, this will be streaming current. And it is simply represented by SC. We will define these one by one and also deriving the respective relations. So first we will focus on the streaming potential. So from equation basically 10, what we have current is basically equal to L11 delta phi upon T plus L12 delta P upon T. Now we will take a condition if this current is equal to 0. So this is basically equation 10, which I already derived here. So that means we will simply insert in place of current 0, it will be L11 delta phi upon T plus L12 delta P upon T. We can write L11 delta phi upon T will be simply equal to negative of L12 delta P upon T. Here this T and T will go, so we have a simple relation. That means we will write delta phi upon delta P, and we have put current is equal to 0, so we will write it here in the subscript. It will be simply equal to negative of L12 upon L11. So suppose now this is equation 12. What is SP? So it is basically defined as the potential difference per unit pressure difference. Simply we will define it from equation 12. Potential difference per unit pressure difference. Suppose we are considering a state where current is equal to 0 with 0 electrical current. That means this streaming potential is simply the potential difference upon the pressure difference, so which will be equal to negative of L12 upon L11. Okay. Now we will define the second one, which is the electro-osmosis. We will also consider the equation 10 again and equation 11. Equation 10 is current is equal to L11 delta phi upon T plus L12 delta E upon T. So this is equation 10, and equation 11 is J is equal to L12 delta phi upon T plus L22 delta P upon T. Now we will consider a situation if the delta P will be equal to 0. So here this term will go, because delta P will be equal to 0, this term will also go. So we will simply divide this equation with this one. That means we can simply write the electro-osmosis will be equal to then the J upon I. That means we will divide this equation by this. Here we have chosen a condition where change in pressure is equal to 0. It will be simply equal to this much. That means L12 delta phi upon T whole divided by L11 delta phi upon T. So here you will clearly see here the delta phi and delta phi upon T, this will go. So we will simply write it as this electro-osmosis will be simply equal to J upon I, delta P is equal to 0, which will be equal to L12 upon L11. Or we know from Onsager relation this L12 is equal to L21, so you can also rewrite this equation as J upon I can also be written then as equal to L21 upon L11. So this is equation 13. So from this equation we can simply define the electro-osmosis as is simply the flow of matter. That means J, flow of matter per unit electrical current. Per unit electrical current in the state with uniform pressure. That means pressure is same in both the compartments and change in pressure will be simply equal to 0 for this case. Okay. So this way we can define the electro-osmosis. Now we will define the third one, which is called electro-osmotic pressure. So from equation 11 we have this flow of matter J is equal to L12 delta phi upon T plus L22 delta P upon T. So if now this flow of matter J is equal to 0, it will imply that L22, this part we will write first, delta P upon T will be equal to negative of L12 delta phi upon T. So here clearly you can see this T and T will cancel. So we have a simple relation, that means delta P upon, we will divide this one, so it will be delta phi. We have chosen a condition where J is equal to 0, it will be equal to this much, negative of L12 upon this one, L2. So this is equation 14. That means we can define the electro-osmotic pressure as the pressure difference per unit potential difference. Potential difference when the flow J is 0. So basically this electro-osmotic pressure is simply the pressure difference, that means delta P upon the potential difference, that means the delta phi, when the flow J is equal to 0. This will be equal to minus L12 upon L22. So the last one, that is called the streaming current. Now from equation 10 and 11 again, we can simply write I is equal to L11 delta phi upon T plus L12 delta P upon T. This is equation 10, and J is equal to L12 delta phi upon T plus L22 delta P upon T. Now if the change in potential is equal to 0, that means here this term will be equal to 0, this term will also be equal to 0, and this term will be equal to 0. So we can simply divide now I upon J when delta phi is equal to 0 will be simply equal to L12 delta P upon T and L22 delta P upon T. So this and this will go, so it will be simply equal to then L12 upon L22. So this is equation. That means we can simply define the streaming current. It is basically the electric current flux per unit matter flux when when the electrical potential difference is tends to 0, tends to 0. Also, from equation 12 and 13, if we look carefully, the delta phi upon delta p at I is equal to 0 will be equal to negative of J upon I delta p is equal to 0, because when we compare the phenomenological coefficient ratios, we will see this part is basically equal to this part. That means simply we can simply write the SP is equal to negative of EOP. So this is equation 16. This equation is also known as Saxon's relation. Now if we compare equation 14 and equation 15, we get delta P upon delta phi when the flow of matter is equal to 0 is basically equal to minus I upon J delta phi is equal to 0. That means we can simply say the electro-osmotic pressure is basically equal to the negative of stream current. This is equation 17. So these equations, that means 16 and 17, they basically relate an osmotic effect to a streaming effect. Okay, thank you.